Your house has a heat source built directly into its structure that your AC system can never overcome. Not the outdoor air temperature, not poor insulation, not single pane windows, your roof. Right now, on any summer day above 85 degrees, your dark asphalt shingle roof is absorbing between 85 and 95% of every photon of sunlight, hitting it and converting that energy directly into heat. That heat conducts through your roof deck into your attic. Your attic temperature climbs to 140 degrees or higher by mid-afternoon. That 140-degree air mass then radiates heat downward through every inch of your ceiling, 24 hours a day, all season long. Your AC isn't fighting the outdoor temperature. Your AC is fighting your own roof. And it's losing that fight every single day you run it. There's a $7 powder sitting on every hardware store shelf right now that stops that process at the source. Not reduces it, stops it. And the physics behind why it works is more elegant than anything the cooling industry has ever sold you. Before we go further, here's a question worth locking in. What percentage of sunlight does standard commercial white paint actually reflect? Is it A, 50%, B, 75%, C, 80%, or D, 98%? Drop your answer in the comments below and we'll come back to this. Number 1, what your roof is actually doing and why your AC is already behind before it turns on. Most people believe their air conditioner cools their house by pumping in cold air. That is not what it does at all. Your AC unit removes heat that is already inside your home and dumps it outside. It is a heat mover, not a heat stopper. And here is the core physics problem your AC company has never once mentioned in any marketing material, any installation guide, or any efficiency recommendation they have ever produced. While your AC is moving heat out one end of your house, your roof is continuously pouring it straight back in through the other. A standard asphalt shingle roof has a solar reflectance index between 5 and 10%. That means it absorbs 90 to 95% of every photon of solar radiation that strikes it during daylight hours. That absorbed radiation converts directly to thermal energy and conducts through your roof deck into the attic below within minutes of initial exposure. Attic temperatures in American climates with direct sun regularly hit between 130 and 160 degrees by mid-afternoon on a standard summer day. That heat mass then radiates downward through your ceiling insulation and into your living space continuously, not just while the sun is shining. For hours after sunset, as the absorbed heat slowly dissipates into the cooler interior below. Call this the solar loading trap. Your AC is running constantly on hot days, not because the outdoor air temperature is too high for it to handle. It is running constantly because your roof is functioning as a continuous heat injector directly above every room in your house. The moment sunlight strikes your dark roof surface, your AC is already behind. It is spending the majority of its operating energy just counteracting a heat source it was never designed to fight, sitting 3 feet above your ceiling. Here's a question that helps lock this in before we go further into the physics. On a summer day when the outdoor temperature is 95 degrees Fahrenheit, what temperature does a standard dark asphalt shingle roof surface actually reach? Is it A, 100 degrees, B, 120 degrees, C, 150 degrees, or D, 175 degrees? Think about that before we hit the mechanism that stops it. Number 2, the solar bounce effect and why reflectance is the most powerful cooling technology ever discovered. Every surface on Earth has a property called solar reflectance, which measures what percentage of incoming solar radiation a surface bounces back into the atmosphere instead of absorbing it. Your dark asphalt roof sits at a solar reflectance of 5 to 10%. Standard commercial white paint, the coating on most white commercial rooftops across America, reflects approximately 80% of incoming solar radiation. That 80% sounds effective until you run the actual thermal numbers on a residential scale. Even at 80% reflectance, the remaining 20% absorption still generates significant heat load across a full residential roof surface. A 1,000 square foot roof receiving direct summer sun still absorbs the thermal equivalent of 2 to 3 kilowatts of continuous heat energy, even with commercial white paint applied and performing at its rated specification. The $7 powder, hydrated lime, calcium hydroxide, the exact material that Minoan builders were applying to their structures on the island of Crete in 1500 BC, reflects between 95 and 98% of all incoming solar radiation. That is the solar bounce effect. And at that reflectance level, the physics stops being about reduction and starts being about elimination. A 1973 study conducted at Lawrence Berkeley National Laboratory demonstrated this mechanism directly. Researchers applied simple powdered limestone mixed with water to a flat rooftop. The exact formulation that Mediterranean builders had been using continuously for 3,000 years. The roof surface dropped 40 degrees in surface temperature compared to an identical dark roof immediately adjacent to it. Interior building temperatures fell 8 degrees without any mechanical cooling operating. 0 air conditioning running. 8 degrees of interior temperature reduction from powder and water applied in an afternoon. The correct answer to the first quiz question is D, 98%. Commercial white paint reaches 80%. Hydrated lime reaches 95 to 98%. That 15 to 18 percentage point difference in reflectance produces disproportionately large differences in actual thermal outcome because of the physics of radiative cooling that operates at the high end of the reflectance scale. Number 3, the Purdue proof and the number that made a $300 billion industry uncomfortable. In 2021, Professor Julien Rouen at Purdue University set out to engineer the most reflective surface ever created in a laboratory setting. His research team was testing the absolute physical ceiling of what ultra-high reflectance surfaces could do to building thermal loads. The formula they produced uses barium sulfate particles engineered to scatter light uniformly across all solar wavelengths simultaneously. The resulting surface reflects 98.1% of all incoming solar radiation. The Guinness Book of World Records certified it as the whitest surface ever created by human hands. The peer-reviewed paper in ACS Applied Materials confirmed the numbers under full scientific scrutiny. But the figure that matters most for anyone trying to cool a building is the one Rouen calculated from his field measurements. Coating 1,000 square feet of rooftop with this ultra-high reflectance formula generates 10 kilowatts of continuous cooling power. A standard residential central air conditioning system operates at 3 to 5 kilowatts of output capacity. The coating wins by a factor of 2 to 3 against the machine without consuming a single watt of electricity. Now here's the physics connection that ties Professor Rouen's laboratory work directly back to the $7 bag at your hardware store. The mechanism behind ultra-white paint and the mechanism behind hydrated lime are identical at their physical foundation. Both work through the same two processes that your AC system uses neither of. Process 1 is shortwave solar rejection, bouncing incoming visible light and near-infrared radiation back into the atmosphere before it ever converts to heat inside your structure. Your AC system has no ability to prevent this conversion. It can only move the heat after it has already formed. Process 2 is long-wave infrared emission, radiating heat that is already stored in the surface material back out toward the sky overhead, even during peak daytime hours, even when the outdoor air temperature is at its maximum for the day. The second process is called radiative sky cooling, and it is the reason Professor Rouen's test surfaces actually measured below ambient air temperature during direct midday sun exposure. The surface was not simply rejecting incoming heat. It was actively pumping stored heat upward into the atmosphere above it through infrared radiation. Your AC moves heat sideways, out of your house and into the outdoor air beside it. High reflectance lime moves heat vertically, radiating it straight up toward the sky. The sky above your roof, even on the hottest summer day, operates at an effective radiative temperature of -50 to -70 degrees Fahrenheit as a heat sink for long-wave infrared radiation. Your AC on a 95-degree day is dumping heat into 95-degree outdoor air. The lime on your roof is dumping heat into a heat sink that operates near absolute zero. Call this the sky dump advantage. And it is the reason the ancient Mediterranean civilizations that perfected lime wash architecture ran this system at village scale for thousands of years before anyone understood the thermodynamics behind it. The correct answer to the second quiz question is C, 150 to 160 degrees. A standard dark asphalt shingle roof surface reaches 150 to 165 degrees on a 95-degree summer day. Your AC is fighting that heat source from below while it pours continuously from above. Number 4, the HOA rule that is not about aesthetics. Homeowner associations across dozens of American states maintain explicit rules in their governing documents prohibiting highly reflective or white roofing surfaces. Their rule books mandate earth tones, browns, tans, and dark grays. Specifically, the exact colors that sit at 5 to 10% solar reflectance and mathematically guarantee maximum solar heat absorption through the roof surface. The global HVAC market generates over $130 billion annually. The global paint and coatings market generates over $200 billion annually. Hydrated lime is a commodity mineral compound that cannot be patented and cannot be trademarked. You cannot build a subscription revenue model around a powder that costs $7 a bag and performs at the physical ceiling of reflectance science. These rules did not require any coordinated effort to exist. They required building standards written when this physics was either not understood or not convenient to apply. The physics does not care about HOA rules. Number 5, the thermal mass problem and why the roof is just the beginning. Reflective coatings solve the solar loading trap by stopping incoming shortwave radiation from converting to heat inside your structure. But your home is also storing heat in its thermal mass. The concrete, brick, drywall, and framing lumber that makes up your wall and floor structure absorbs heat during peak solar hours and releases it slowly back into your living space through the evening and overnight hours. This is the thermal mass trap. Even a perfectly reflective roof coating addresses only the overhead heat injection. Your south-facing wall receives direct sun exposure for the longest arc of any surface on your home. Your east and west walls take peak solar loading during morning and afternoon hours, respectively. The Mediterranean builders who developed lime wash architecture over thousands of years of observation did not limit their application to rooftops. They painted every exterior surface of every structure completely white. The physics of that total approach compounds across all surfaces simultaneously. A south-facing wall with 5% solar reflectance absorbs peak afternoon sun and turns your wall into a slow-release thermal battery radiating heat inward through the evening. A south-facing wall coated with hydrated lime at 95% reflectance converts that same exposure into near-zero heat gain. Stack that thermal reduction across every exterior surface of your structure, and the combined effect exceeds what your AC system can realistically compensate for during peak summer heat. The total material cost of treating every exterior surface of a standard American home with hydrated lime runs under $50. That is the number that makes full system passive cooling economically rational, compared to operating mechanical cooling around the clock all summer. Number 6. Exactly what you do with this starting today. One 50-pound bag of Type S hydrated lime costs between $7 and $14 at any hardware store in America. The active compound is calcium hydroxide. That is the whitening agent and the reflective physics engine in the same material. Mix 1 part lime powder to 2 parts water and stir until the consistency looks like thin milk rather than paste or thick mud. This formulation is called a lime wash. It is the exact recipe that Mediterranean and Middle Eastern builders have applied continuously for 40 centuries. Apply with a thick nap roller or a wide brush to a clean, dry roof surface in 2 full coats. Let the first coat dry completely overnight before applying the second coat. The total material cost for an average American roof at 1,200 square feet runs between $14 and $28, depending on your local hardware store pricing. A homeowner in Central Texas applied this formula and installed a digital thermometer probe in his attic before and after the treatment. Before the lime wash, his attic measured 143 degrees at peak afternoon on a 97-degree day. After the treatment, his attic measured 97 degrees at the same time on a comparable weather day. A 46-degree drop in attic temperature from 2 bags of powder applied in one afternoon. His indoor living space temperature fell 10 degrees without the AC running at its full load cycle. His estimated electricity cost reduction for that single summer season exceeded $1,200. Compare that against a new central AC installation running between $5,000 and $15,000 up front, plus $150 or more in monthly electricity operating costs every summer season. The lime wash requires reapplication every 2 to 3 years as weathering gradually reduces reflectance back toward baseline. Each reapplication costs $14 to $28 and 1 afternoon of work. The physics resets completely with each fresh coat. The Greeks figured this out before written language existed as a formal system. Professor Ruin proved the exact physical mechanism in a peer-reviewed laboratory in 2021. The powder has been sitting on the shelf at your hardware store the entire time for $7 a bag. Your roof is a 140-degree heat injector pumping thermal energy directly through your ceiling every hour of every summer day. The $7 fix converts it into a radiative cooling surface that dumps heat toward space instead of into your living room. That is the complete physics of why a $7 bag beats a $3,000 machine. And now you have the mechanism to understand exactly why it works at every layer, from the Greek island villages to the Purdue laboratory. If you want to go deeper on the survival applications of passive thermal management, the next video covers the underground cooling systems that keep structures habitable in extreme heat without any power source at all. The earth physics behind that system is the thermal mass principle taken to its logical conclusion.